closest neighbor to Earth. Presently the focus of man's greatest scientific adventure, the first celestial body that will be explored by man. Landing men on the moon will be a truly great achievement, but only the beginning of a new era in space exploration. No one can predict the exact missions that will follow in the years and decades ahead. But the most exciting possibilities will require the acceleration and deceleration of very heavy loads, such as the maneuvering of large Earth-orbiting spacecraft. The transportation of large amounts of equipment and supplies to the lunar surface, and the sending of heavy spacecraft to the planets. Today's missions are being accomplished with rockets that burn chemical fuels. But chemical fuels are heavy, and the cost of putting each pound into Earth orbit is very high. Nuclear rockets, when perfected, can provide the same propulsion energy with less overall weight. They will expand our ability to explore space. This is the story. This is Saturn V, the most powerful launch vehicle being built by the United States. A three-stage rocket that will place the Apollo spacecraft in the vicinity of the moon. The total weight of Saturn V is about 6 million pounds. Its three stages have chemical engines that burn fuel to generate thrust. The first and second stages provide most of the energy needed to put the third stage and the payload, about 250,000 pounds, into Earth orbit. At present, only chemical rockets can provide the high thrust needed to do this job. The third stage accelerates the payload to the velocity needed to get it to its destination. Here, travel time and payload weight are determined by the efficiency with which the propellant is converted into thrust. By substituting a nuclear third stage for Saturn V, the velocity of a given payload can be greatly increased, cutting travel time for some missions in half. This is particularly important in sending deep space probes to Jupiter and beyond. Or if shortening travel time is not essential, propellant weight can be traded off for an increased payload weight. This is important for a lunar supply mission, Earth orbital operations, and some unmanned missions to the planets. Why is the nuclear rocket so much better than the chemical rocket? In rocket propulsion, exhaust velocity determines propulsion efficiency. At a given temperature, the lighter the exhaust gas, the higher the exhaust velocity. And the higher the exhaust velocity, the more thrust is generated for each pound of propellant consumed per second. The nuclear rocket merely heats hydrogen, the lightest element of all, and expels it at tremendous velocity. Chemical rockets burn fuel to produce exhaust gases that contain heavier elements. So at the same exhaust temperature, the exhaust velocity is much lower, and each pound consumed per second produces less thrust. Rocket efficiency is stated in seconds of specific impulse. This refers to the time in seconds that 1 pound of propellant will deliver 1 pound of thrust. The higher the seconds of specific impulse, the greater the propellant economy. Our best chemical rockets of today are limited to a specific impulse of about 450 seconds, and only slight improvement can be expected. On the other hand, full-scale nuclear reactor tests have achieved 800 seconds, and laboratory tests promise even more, perhaps as much as 900 seconds. This means the nuclear rocket, with its lightweight, high-velocity exhaust, will use propellant about twice as efficiently as chemical rockets. This, then, is the principal advantage of nuclear propulsion.
It was at the AEC's Los Alamos Scientific Laboratory, high in the mountains of New Mexico, that the first steps were taken. Here, in the mid-1950s, scientists set about to determine if nuclear energy really could be used to provide rocket propulsion. Theoretical studies and early experimental work revealed many problems that would have to be solved. Problems in reactor design, material, radiation, structures, control, to name but a few. The nuclear rocket was found to be feasible. A series of experimental reactors was planned to convert theory into workable hardware. Optimum reactor designs were worked out by analysis. Prototypes were built. A comprehensive test program was started. These reactors, called Kiwi, were to be used to prove out design and operational concepts. They would be built only for ground testing. All Kiwi power tests took place at the Nuclear Rocket Development Station at Jackass Flats, Nevada. Here in the desert, scientists and engineers checked the actual performance at various power levels and for various time periods. Each experimental Kiwi reactor was received in sections, assembled and checked out in a special reactor maintenance, assembly, and disassembly building called simply RMAD. When the reactor was ready for testing, it was placed nozzle up on a special rail car and delivered to the test stand a mile or so away. This car could be controlled from a remote station. Liquid hydrogen from nearby storage tanks was pumped through the reactor. First tests were begun in 1959 and were run to the 100 megawatt level, about 1/10 of Kiwi's ultimate goal of 1,000 megawatts. Later tests, beginning in 1962, operated at the full 1,000 megawatts. Films of these early tests show the flaming torch on the test stand that burns off the hydrogen exhaust gas and prevents an explosion hazard to the test facilities. Upon completion of these tests, each reactor, by then radioactive, was transported by remote control back to the RMAD building for disassembly and inspection. Here, men working behind shielded walls used remote-controlled manipulators to remove the components for careful checking and analysis. Each test firing added information that helped scientists evaluate the reactor's performance and enabled them to make adjustments and corrections before the next reactor was assembled. But not all tests showed perfect performance. In this one, for example, the flashing in the exhaust gas indicated a structural breakup caused by excessive vibration. Extensive redesign and testing were needed to correct the flaw. And in this test, a hydrogen leak caused a fire on the test stand. Again, a correction was made. Each test brought the scientists a little closer to the performance they were seeking, until finally, in September 1964, the 8th Kiwi reactor was brought up to full power and held for 8 minutes. And a few weeks later, it was restarted and operated at full power for 2.5 minutes. Specific impulse, about 750 seconds. This concluded the Kiwi test series. It had proved that a nuclear reactor could be built that would power a spacecraft.
The next step, already underway, was to develop complete engine technology. This project was called NERVA, Nuclear Engine for Rocket Vehicle Applications. It was to be a combined industry-government effort headed by the Space Nuclear Propulsion Office, a joint NASA and Atomic Energy Commission activity. The principal contractors were to be Aerojet General Corporation and Westinghouse Astronuclear Laboratory. The NERVA technology reactor, given the letter designation NRX, was essentially the same as Kiwi, but now the contractors had to extend its lifetime and put it into an engine configuration. Here is how the nuclear rocket engine will work. The reactor is a solid core, heat exchange type, cylindrical in shape. Fission of uranium atoms in the core is the source of heat. A reflector made of beryllium surrounds the core. The core consists of many graphite elements impregnated with the uranium-235 fuel. The core contains a number of channels running down its length. Hydrogen passing through the channels picks up heat generated by the fission process. The channels are coated with niobium carbide, a material which resists the corrosion that would occur if the hot hydrogen were allowed to come into direct contact with the hot graphite. The hydrogen is stored in a liquid state to achieve the lowest possible volume. The flight model will use about 1/3 of a million gallons for a 30-minute firing. To start the engine, the cold liquid hydrogen at -420 degrees Fahrenheit moves through a pump down to the nozzle, through internal passages in the nozzle walls, and back up inside the reactor pressure shell and reflector. This cools the nozzle, the reactor shell, and the reflector, and at the same time warms the hydrogen. The hydrogen then passes through the hot fuel elements where it is heated to about 4,000 degrees Fahrenheit. From there, it is expanded through the nozzle to provide thrust. The bleed line carries some of the hot hydrogen back to drive the turbo pump. The whole engine system is amazingly compact for a nuclear power source. The reactor works through fission of uranium-235, which constantly emits nuclear particles called neutrons. When reflected back toward the reactor, these particles will set up a chain reaction, generating terrific heat. The heat is controlled by rotating rods installed in the beryllium reflector around the reactor. The rods are also made of beryllium, but one side is coated with boron, which absorbs neutrons. Initially, the rods are turned so the boron side is toward the fuel elements, and sufficient neutrons are absorbed to prevent nuclear fission from starting. Beryllium reflects neutrons. By turning the beryllium side toward the elements, a point is reached where sufficient neutrons are reflected for fission to begin. The amount of heat produced depends upon the position of the rods. Heat increases as more of the beryllium side turns toward the core. When the desired rate of heat production is reached, the rods are turned back to stabilize it. Heat decreases as the rods are turned back. When the boron side absorbs enough neutrons to halt the fission process, heat is no longer generated. These rods can be operated by remote control.
Test facilities for engine components were built near Sacramento, California. The problem? Get adequate performance with minimum weight. The pump must move huge quantities of liquid hydrogen under pressure at -420 degrees Fahrenheit, while the hydrogen-cooled nozzle must expand high-pressure gaseous hydrogen at 4,000 degrees to low pressure. The reactor was designed to meet the structural requirements of ground handling, launch, and spaceflight. In a late 1965 test, it operated intermittently for an hour, including 16 minutes at full power. But in that test, as in all reactor tests before it, the hydrogen had been forced through the reactor by test stand pumping facilities instead of its own turbine-driven pump. In early 1966, the new technology reactor and the chief engine components, including the turbo pump, were assembled for test. It was called a breadboard because they were not arranged as they would be in an actual engine. It would be the first self-starting test, and it was a vital step in the nuclear propulsion concept. This engine test model started perfectly and increased to full power, proving that a nuclear rocket could be started by its own pump. During a 2-month period, it was started and stopped 10 times and operated at different power levels for a total of 110 minutes, 28 minutes at full power. Technology had now advanced to the point where performance limits could be extended. Work was already underway to increase reactor power and operating time. In February 1967, this reactor, the Phoebus 1B, was operated at a power level roughly equivalent to 75,000 pounds of thrust. And in December 1967, this reactor, the NRX A6, was operated at full power for an hour. Also in 1967, a new test stand was completed that would permit a test engine to be fired nozzle down into a vacuum chamber below, at least partially simulating the space environment. In early 1968, the first ground test engine was mounted in the new stand. Its success was a new milestone along the long road leading to a flight engine. Heavy shielding was used in this test engine to protect some of the components from intense radiation. In flight engines, all components will be radiation hardened and less shielding will be needed. These tests will complete the technology for a nuclear rocket engine for application to space missions of the late 1970s and beyond. Its thrust will be approximately 75,000 pounds. For missions that require higher thrust, 2 or more of these engines may be used in a single stage, or several engine stages may be assembled side by side. This versatility will give us the capability to perform a variety of advanced missions.
Someday, a manned trip to Mars and return may become the mission assignment. Exactly how it would be carried out depends upon a number of factors. But here is one way it might be done with nuclear rocket propulsion, using the technology developed for earlier missions. Using several Saturn V launch vehicles, components of the huge spacecraft would be placed into Earth orbit and assembled. Separate nuclear stages might be provided for each major step of the mission. The first stage might consist of 3 clustered rockets for departure from Earth orbit. 2 other nuclear stages consisting of 1 engine each would be used in the vicinity of Mars. The first stage cluster fires to accelerate the spacecraft to the velocity needed to get to Mars in the time that was decided upon, say 200 days. At burnout, the first stage cluster is jettisoned and goes into orbit around the sun. Mid-course correction is made by chemical rockets. About 200 days later, the space vehicle approaches Mars. There it is slowed down by a single nuclear rocket and enters an orbit around the planet. The used second stage is put into a higher Mars orbit than the space vehicle. A chemically powered module departs for the planet's surface. For the first time, men from Earth will set foot on another planet. For the return trip, the module is lifted by chemical power back into a Mars orbit, where it docks with the main space vehicle. The men transfer to the main craft and jettison the module, leaving it in an orbit around Mars. A third nuclear rocket accelerates the vehicle for the return trip. And it is jettisoned. Again, mid-course correction is made chemically. Just before reaching the vicinity of Earth, the crew transfers to a re-entry vehicle and jettisons the large spacecraft. Chemical rockets slow down the vehicle to re-entry speed, and they are jettisoned. After deceleration through the atmosphere, the re-entry vehicle returns to the Earth's surface by parachute. A trip to Mars and back, for centuries a dream of earthbound men, is now much closer to reality. Of course, there are many, many other problems to be solved before such advanced space missions can be attempted. Life support systems for extended space journeys, more accurate space navigation, communication systems, power supplies, and so forth. But any successful advanced mission must begin with propulsion, the power to get there and back. Lower overall weight, larger payloads, shorter travel time. These are the chief advantages of nuclear propulsion. The technology needed to build a nuclear rocket is well advanced. It will be available when this nation determines its next great objective in space.